last time, our second lesson today? No? You still follow me? So we said we would like to calculate atoms with electrons around them. We said some people do it without the electrons. We come back to this aspect a little bit later, but we would like now to really understand, starting from the Schrodinger equation, what we can do. Okay? And we said the Schrodinger equation, which we've written, it's not really exact because it is non-relativistic, but it's already pretty good. And we will now try to get a handle on it. Okay? And I just repeat from last time the Hamiltonian which we had. You have this already, so you don't need to copy it. So the Hamiltonian had sum over all electrons, h squared divided by 2m radians square of this. Then we had sum over all nuclei, h bar squared divided by 2m nucleus gradient with respect to the nucleus squared. Then we had the minus sign, obviously. Then we had repulsive energies, which was 1/2 sum I and j over E squared divided by I minus rj. Then we have plus 1/2 sum I and j I j e squared divided by I j. And we have minus sum I e squared divided by I. Okay, so this is our complete Hamiltonian. You might remember from last time that we have said, okay, 2 kinetic energies, 2 repulsive energies, and 1 attractive energy. And we have said, if this Hamiltonian was such that this term did not exist, then we have terms which act only on nuclei, namely this term and this term. And we would have terms which act only on electrons, the first term and this term. And then we could separate our wave function into a product of something which depends on electronic coordinates or electronic degrees of freedom, and one wave function which depends only on nuclear degrees of freedom. We cannot do this because we have this term which is mixed between the two. And this is not a simple sum of something electronic and nuclear, it's a complicated dependence. So this term here forbids us to write the wave function as a product. However, in physics, what we most of the time, when we have a term which looks difficult or which we don't like or whatever, we always try to neglect it. Okay, so but here also we have said we cannot just neglect this term, because if we neglect this, then everything is repulsive and our matter flies apart. So we cannot neglect it. However, we have said last time, okay, we could, and this was one of the 2 comments which I made, we could say that if this term wasn't here, then the overall Hamiltonian would be of the form something electronic plus something nuclear. So the idea is that we can perhaps search for a solution which looks similar to something which is a product function. It will not be exactly product, but it might look similar. Okay? And this is what we are going to do now. So what we are going to do today is called the Born-Oppenheimer Approximation. Sometimes this is also called the adiabatic approximation. As the title already tells you, it's an approximation. So what we will be doing will not be exact, but we will in a very well precise form say this. Let me just say, so Born and Oppenheimer, obviously 2 famous scientists. I should mention here, because we are in ICTP, Mr. Oppenheimer, he has or he has had some clear affiliation with ICTP, with this thing here. This is also why we have one meeting room in the second floor. There's the Oppenheimer meeting room. It's named after Oppenheimer because he was the first president of ICTP Scientific Council. So when Abdus Salam created ICTP, he created a consultory board, which exists until today, which is the Scientific Council. And the first president of this board, which is giving tips to ICTP how to do better, was Mr. Oppenheimer himself. So he was here several times. Like many of the famous scientists you learn about have been here. For example, Mr. Dirac, he has been very often here. So the Dirac of the Dirac notation and all this, he has been here. And you might have seen that the stairs which lead to the Miramar Park, they are called Dirac stairs. And this is for a reason, because at the time when Dirac was here, at least at his first visits, these stairs did not yet exist, but the park existed, okay? And there was not yet the fence and all these things which are here. So apparently Dirac, who liked a lot this park, he always went from this building into the park, climbing up the hill and sometimes coming down on his trousers like this. And so this hill here was very famous for Dirac climbing up and down. And then at a certain point they decided to make stairs, and obviously they were called the Dirac stairs. Okay, so, I mean, these things have a real reason, and today so we do Born-Oppenheimer. I'm not aware of any affiliation of Born with ICTP, but Oppenheimer clearly had affiliation with ICTP. But he did not invent this approximation here. Okay, so what is it? So we said, apart from this term, we would have a product. So the idea is we look for a solution which looks nearly like it. Okay? So we are searching for a solution, so for a wave function of the following form. We write our complete wave function, which is a function of electronic and nuclear degrees of freedom. We are looking for it as a product of two kinds of wave functions. Okay, so we write this as a wave function phi, capital Phi, which will depend on all electronic wave function and all nuclear, times a wave function which I call Xi, which depends on nuclear degrees of freedom. Okay, so now I should say something about this. Is what one calls an ansatz. Okay, an ansatz means one writes a solution in a given form. If we really had the Hamiltonian as a sum of electronic and nuclear parts, then we could have written phi, which depends only on electronic degrees of freedom, times psi, which depends only on nuclear degrees of freedom. This would have been what we would desire. We cannot do this, but here, so we are writing something similar. We are writing as a product of phi, but we have to allow that phi also depends on the nuclear degrees of freedom. While Xi, we say this is really a purely nuclear wave function. It will not depend in any way on electronic degrees of freedom. Okay. Now, so writing this is not an approximation. So this is not a Born-Oppenheimer approximation, because in principle, if you write this, you could always choose that Xi is identical to 1. Okay, and then you have the exact wave function. So Xi exact 1 is possible here. So how we define Xi and phi, we will see later when the equations come down. Okay, so this is not this is certainly always possible to write the wave function as something which depends only on nuclear degrees of freedom and something which depends on everything. In the worst of all cases, as I said, this will be a trivial function, and all the interesting stuff might be here. Okay? So no approximation done yet. We are just writing.
Excuse me.
Yes.
Just looking at the Hamiltonian, the nuclear and the electronic degrees of freedom has kind of equal weightage. Because in the first four things, they are like kind of symmetric. In the last one,
yes,
they are just the difference. So we are searching for this. Why aren't we searching for R big R and chi of small r?
Because with this way, you will see that we find out something. I mean, what breaks the symmetry between electrons and nuclei in the Hamiltonian is obviously the very large mass. And we will come back to my comment number 1 or 2 of last time, that if the kinetic energy term is very small, then the solution will look like a delta function in space. Okay? So since we already know that one of the two solutions will look very much like delta functions, namely the nuclear one, which will be much more localized than the electrons, this breaks the symmetry in the solution. And I already know that how the things will look like. Our total wave function will be something, the dependence on the nuclear will be looking like delta functions, therefore I take this already out. Okay. So before doing any calculations, I already know kind of how the solutions will look like, and this is why I make it in this way. The electrons will never look like delta peaks, so therefore I leave them in the more complicated part of the solution. But in principle, at this point, I could also have said, yes, phi, which depends only on electrons, and psi, which depends on both. So nothing is wrong with this. So we have this ansatz, and now we look at one particular term, which is this one. So this, we said, is the kinetic energy of the nuclei, but this here was T of the electrons. And we just look at what is Tn, because here will come in our approximation. So what is this Tn? It is acting on this wave function, so we have minus sum over all nuclei, h bar square divided by 2ni, and then we have the second derivative acting on phi of ri. Times psi of okay. So now we act with the second derivative on a product, and we know how this goes. The derivative will act either on this, or on this, or on both. Okay, so we write all these terms which come out. So this here is then minus sum over I, h bar square over 2ni. And now come several terms. First one where we act with the second derivative on psi. So here we can write phi of ri times the second derivative with respect to nuclei on psi. This is one of the terms. Then we have the opposite one, where we have psi, which depends only on the nuclear degrees of freedom, times the second derivative of phi. Okay. And then we have the mixed term, where we plus 2 times gradient psi scalar product gradient of phi. So in the kinetic energy of the nuclei, we have these three terms. And now we come to what is called the Born-Oppenheimer or adiabatic approximation. We will understand the word adiabatic in the very end when we see what results from it. But we have the following idea. So when we have written this ansatz, if this is a useful ansatz, then we can hope that all the main dependence on the nuclear degrees of freedom of the wave function will be somehow incorporated in psi. So we will try to get as much of the nuclear dependence into psi, and this here to make it as little dependent on the nuclear coordinates as possible. Okay, so this is our goal. We know the wave function is not a product. If it was really a product, because of the last term wasn't here, then we could simply say, okay, only this depends on nuclear degrees of freedom. But we know, because of the last term, this will also depend on it. But we can hope that the dependence is somehow weak or slow or whatever. Okay? I mean, we have to check later if this is a good approximation or not, but this is what we try to say. So if we say that most of the dependence, and we know the wave function will look like delta functions, and if we put all the delta function shapes into psi, then our hope is that phi will depend in some sense weakly on the nuclear degrees of freedom. Okay? If it depends weakly, it means that the derivative of the wave function with respect to the nuclear degrees of freedom might be weak, okay, with respect to the dependence of psi. Okay. So the Born-Oppenheimer approximation amounts to saying we neglect this term and this term. And this is now clearly an approximation. Okay? So while this here is still exact, neglecting these two dependencies is an approximation. And we will obviously now have to check later if this is good or bad as an approximation. But this is so. This here is our approximation. Neglecting this here and this here, this is the approximation. The famous Born-Oppenheimer approximation. So the Born-Oppenheimer approximation, what it really goes into is into the kinetic energy of the nuclei. And there we neglect two given terms. And now this has the nice advantage that we can simplify our overall equation, as you will see in a minute. Because imagine now you have the complete Hamiltonian. You act on with the complete Hamiltonian on phi times psi. Okay? You know, electronic dependencies are only here. And we also know now when this term here will act on phi psi, it will act on it only on psi, and phi will be not touched by this term. Okay? So, if you write all these terms together, then one arrives at something which is quite interesting. Now I wonder which part. Have you copied this? Can I erase this? Because I would like to keep the Hamiltonian and have space for some. Because now what we obtain is the kinetic energy of the nuclear, h bar squared divided by 2 I with the sum over I, gradient I squared acting on the nuclear wave function. Then we obtain 1/2 J Ci Cj e squared divided by J times Xi of I plus a function which I call U, which depends on all the nuclear degrees of freedom. Multiply by Xi is V times Xi. So now you might say, where is the phi? Where are the electrons? Because here you see now, this is an equation. There is no phi anymore. You have only the nuclear wave function. Okay. And apparently the electrons have disappeared from it. What kind of dirty trick did I play? I mean, I used this here times phi psi is E times phi psi. Okay. The next step I've done without writing is, I've multiplied this whole equation from the left with a phi, so only the electronic part, complex conjugate. And I integrated this whole thing about all electronic degrees of freedom. So then it happens in this part here will reappear in a minute because it is hidden here. So this here will reappear. But this part here was phi times this here. But I've multiplied with phi star. I integrate, so phi star, since it's normalized, goes to 1. Okay? So this term here has become simply this here. This term here will reappear in a second, because I have hidden it here. This term is again, this is only acting on nuclear degrees of freedom, so it was acting on the psi, and it is here. The phi, the electronic part, I have taken it to the other side, and I integrated over all electrons, and therefore it is again 1. And the mixed part will reappear also in a second. So I have an equation like this, and look what it looks like. It's an equation which contains only a nuclear wave function, pending nothing, no electrons anymore there. And it looks like a kinetic energy, a normal kinetic energy, like an average Schrodinger equation. This here is the Coulomb interaction, so it's the nuclear-nuclear interaction, okay? And then there is some u, which I will now define to you. Some u, and this will obviously somehow depend on the electrons. So there is some potential energy on this here. Okay? So we have a Hamiltonian, or we have a Schrodinger equation for the nuclei, which has a nuclear wave function, and it has kinetic energy, and nuclear-nuclear pairwise interaction, and something which is like a potential for every nuclear coordinates you can have. And now I must also, this is a nuclear Schrodinger and now this u, which I've just written here, what is it? So u, or I write it down because here I will write something else. So u for all nuclear degrees of freedom. It is the integral d3n about all electronic degrees of freedom. So I'm integrating out all electronic coordinates of phi star, which depends on all the electrons, all the nuclei. So there is some electronic wave function here. I'm integrating phi star times, and now all these terms which we have had. So minus h bar squared divided by 2m, gradient squared phi, plus 1/2 sum I j with a prime, e squared divided by ri minus rj, minus sum I z I squared divided by ri times phi So this is the definition of something which depends on all nuclear coordinates, as we have written it, but all electronic degrees of freedom go away because we are integrating over all possible coordinates of all electrons. The phi, as I've said before, goes away. In the other terms, the phi goes away because we have just phi star times phi, and since the wave function is normalized, it goes to 1. All these terms here are those which have an operator which acts explicitly on electrons. You see here you have an operator, this here acts on electrons, this acts on electrons. Okay? So here I could not put phi on the other side and integrate this to 1. This here is something which one has to calculate in principle, but it is well defined. And you see here that the coordinates of the nuclei are whatever they are. They are given as numbers if you want. And for every nuclear configuration, meaning where the atoms are, you integrate over all positions for all electrons, phi, an electronic wave function, phi star times phi. with something in between.
Okay. For the sum.
Sorry?
In the energy, like cut T sum.
Here, the sum you here is here. Yeah. Okay. So, I mean, I do not say this is easy to calculate this integral or this is easily solvable as we will see, but it is well defined. Okay. So this Born-Oppenheimer approximation, where we have done something to the definition of the nuclear kinetic energy, it has allowed us to write this equation where this term here, which is well defined, appears. And in order to calculate this u here, what do we have to do? Well, we have to solve this Schrodinger equation because we need phi. Okay? In order to calculate u for a given set of coordinates, we need to obtain phi for these coordinates. So how do we obtain phi? Well, this here is again a Schrodinger equation. It's some electronic Hamiltonian times an electronic wave function. Okay? So this equation here is something very similar because we obtain an equation which is the sum over electrons, h plus square over 2m, gradient square I times phi, which depends on all these kind of things, r plus 1/2 I j prime x squared divided by r I minus r j. Sorry, I should not have. No, okay. I r. So with this term, and now minus some I z I e squared. This is equals to So in order to calculate this u in the nuclear Schrodinger equation, we have to solve this Schrodinger equation for the electrons. And this is the electronic Schrodinger equation. Now you might ask, what have we gained by doing this? Because, okay, we transferred one Schrodinger equation from the beginning into two Schrodinger equations, one nuclear, one electronic. Okay? So, what did we gain? Because here still we have phi, which is a complicated function of both electrons and nuclei. It's not that here we have a wave function which depends only on nuclei, and here we have one which depends only on electrons. So it seems that still here there is a mixed thing, no? But no, we have gained a lot, because in this Schrodinger and the second Schrodinger equation for phi, you discover that there is no kinetic energy acting on phi. There is no derivative with respect to the nuclei in this equation here. The only kinetic term here acts on the electronic part. In the second equation, there is no kinetic energy acting on the nuclei, because we have precisely neglected them in the Born-Oppenheimer approximation. What does this mean? Well, remember my stupid comment from yesterday. If in a Schrodinger equation there would be no kinetic energy term, the solutions look like delta functions. Exactly. Okay? So here you have a Schrodinger equation with no kinetic energy acting on the nuclei. So we know already the dependence of this phi here on the nuclei will be simply trivial. Wherever there is a nucleus, there is a delta peak. Okay? So this is, therefore, all the quantum nature which appears here, the quantum nature is which makes everything non-classical. All the quantum nature here is purely on the electronic side, because you have a kinetic energy only for the electrons. It is as if in the second equation, h bar was 0 for the nuclei. Okay? So this is the big thing we have formed. We have one equation where all quantum mechanical stuff is on the nuclei. In the second equation, all quantum mechanical stuff is on the electrons. And here in this second equation, what you find is that the nuclear positions appear purely as parameters. But here I've written this here. You could have told me this is Ri minus F. Okay. The only point here where the nuclei intervene in this Schrodinger equation is by the position. So you have an electronic problem where nuclei are simply given by fixed positions. And this is what if someone does, I'm doing electronic structure theory, I'm solving the electronic problem, it means one is looking at this equation here, and one defines beforehand where my atoms are. I have a carbon atom here, a hydrogen there, an oxygen there, and so on. For given nuclear positions, you solve what the electrons are doing quantum mechanically. And then in principle, once you have solved this, you obtain the many-body electronic wave function. Once you know phi, then you can calculate for this set of positions, this quantity u, because here now everything is well defined. Once you know u, you calculate this for many possible positions, and you have your nuclear Schrodinger equation well defined. Okay? So what has the Born-Oppenheimer approximation allowed us to do? It has allowed us to separate the original problem, which is a very complicated mixture between electronic quantum effects and nuclear quantum effects, into two equations. Here all quantum stuff is on the nuclei, here everything on the electrons. And this is a huge gain in simplicity. Now, some people sometimes think or hear or deduce or wrongly by saying, Born-Oppenheimer approximation means we are treating nuclear classically. And this is wrong, because you see, the Born-Oppenheimer approximation does not say nuclear classical. No, there is a Schrodinger equation for the nuclei, so you can have nuclei which are wave functions, wave packets, and so on. Where does it come from, this wrong conception of some people that Born-Oppenheimer approximation means nuclear classical? It comes from the fact that those people mainly work in electronic structure, so mainly work on the second equation. And if you work only on the second equation, yes, then obviously here the way nuclei intervene is purely classical because only their position matters. Okay. So if you really solve, and the rest or the main part of my course is on the electronic part because this class is about electronic structure. In this equation, yes, it looks as if nuclei are classical things. But this is not due to the Schrodinger equation, due to the Born-Oppenheimer approximation. It's because our choice to focus on how to solve this. But in principle, you do this approximation, and then you have two equations. And there's, in principle, all kinds of nuclear effects are still included here. Okay? So you have quantum effects also on the nuclei. Yes?
So if you are focusing on the second equation,
yes.
Then how will you have the approximate solution for the above equation, the main one? I mean, without carrying it to the...
and I think this might become clear in a minute when because I will now talk a little bit about this equation. Okay? So we agree that at least conceptually what we need to do is we have to solve for every possible combination of nuclear positions this equation. Having solved it, we know this, and we know u, and therefore we can then do this equation here. Okay? So conceptually it is clear what we need to do. You can all imagine that it's a lot of work, and probably we cannot do it in a finite amount of time, but at least mathematically what we need to do is clear. Is it clear? Okay, good. So we have done this. We have two things. So now let's have a little look at this here, because this equation here is something which is the basis of also a lot of concepts which you have certainly heard about. Because so I've taken away the electrons, we will come back to them soon enough, and we are looking at this equation here. And here this introduces to us the concept of a potential energy surface. So you have certainly seen many times graphs which look like this. Here we have some R, and then you might have some graph which essentially looks like this here, and like this. Here you might have some R naught. Here you might have some E. Can anyone say in which context you've seen graphs which look like this? Certainly have seen it.
Yeah, the potential of electron around the atom.
Oh. Sorry, I didn't hear it.
Coulomb.
No, a Coulomb potential I would draw it not like this. A Coulomb potential I would draw it like this.
And Van der Waals.
Huh?
Van der Waals.
Van der Waals might be, but this is something else.
Potential, the one that holds electrons in the atom.
We should not talk about electrons in this context, in fact. But Lennard Jones, who said Lennard Jones? You, okay. So this is, for example, so a Lennard Jones potential has this shape. But generally this shape is much more general. So Lennard Jones is one example of it, but there can be others. So, and in which context do you hear of Lennard Jones? Well, when you do typically molecular dynamics or something. Okay? So you have your molecules, you have your atomic positions, and then you say the atoms interact pairwise. They interact pairwise with a potential like this. A potential like this means if the distance is very, very large, the interaction is zero. As you bring two atoms more closely to each other, then it will start to bend down. Bending down means it's attractive because the system wants to minimize the energy. So you have a force to bring them together. Here, typically, this is modeled as going like -1 over R to the 6th power. In Lennard Jones, it is like this. You know why? This is -1 over R6. For Van der Waals interaction, because people know that at long distance, neutral systems, they interact via Van der Waals, and it goes with a distance depends like 1 over R6. Then at a certain distance, where the chemical bonding happens, the system is in a minimum energy, which I called here E naught. When they are at an equilibrium, so in equilibrium, the two atoms would like to stay like this. And if you push them closer together, then they repel each other, because after all, they have nuclei which repel each other, and they repel each other very strongly. So typically in equilibrium, your system will be here. If you remove it away from equilibrium, the energy goes up. So the curvature here is linked to the vibrational frequencies of the system. So this is a typical thing one has in classical molecular dynamics. But where does it come from, or where does it fit to our equations? Well, you see here, this thing here, this U, is nothing but a potential energy surface. U obviously depends on all nuclear degrees of freedom at the same time. But if you make the approximation that your matter interacts only pairwise, always one with this and then this with this, then, for example, this U can have an overall shape which looks like this. So one way how many people approach atomistic simulations is by saying, calculating this from first principle by solving for each set of R's the other Schrodinger equation is too complicated, too time consuming, too whatever. We imagine, like Lennard Jones did, how this thing here can look like. Okay? So, and this is then called a potential energy surface. For every configuration of nuclei, one invents how the potential might look like. Lennard Jones is particularly simple. I've told you, if people do classical simulations, then they also include angles between atoms, 3 body terms, 4 body terms. They have 4 so-called force fields. So the notion of potential energy surfaces and of force fields is very tightly related to what we have found out for the nuclear equation. So if you want to get rid of electrons, you simply do not get U from solving some complicated electronic problem, but you put in a U which you parameterize somehow, like you parameterize Lennard Jones or you parameterize some more fancy stuff. So the whole notion of potential energy surfaces goes back to this Schrodinger equation. And now this also tells you, again, no one says that you are forced to do Newton's equation on these potential energy surfaces. You can take this as if it was a harmonic quantum oscillator, and you can calculate, for example, here the ground state quantum energy. You could solve it, and you would find here a nuclear wave function which looks like this, and then here the other solutions to this would look like. I mean, you have learned the harmonic oscillator. Okay? So you can solve this equation with a classical approximation, just Newton's law, and you have the forces. Or you solve inside this potential here, you solve some more complicated equations. Okay? But the point is, this complicated function, which we know is defined really in an ab initio way by knowing what the electrons are doing, you can get rid of the electrons by approximating them. And this is what all the people who do classical simulation or who do not want to do the electronic part, they are working on this. So the notion of potential energy surfaces is this term which we found. And this is extremely successful because effectively the electrons always sit in their ground state. And one always knows if there are two carbons at this and this distance and the carbons have this and that chemical environment, they always behave more or less in the same way. This is why it is such a good approximation to approximate this U with something empirical, which we guess and which one optimizes without ever looking at the electrons. Okay? So this is where this comes from. But, so potential energy surfaces, and then inside such a potential energy surface, you can solve the nuclear problem by two ways. You can do it either classically, or you say, I want to do quantum nuclear physics. So, and then I would like to stress something which I've already said before. In the overall Hamiltonian, what leads to the connection between electrons and nuclei is this term here, which is the attractive term. Note, we have not, at no point, neglected this term. So the Born-Oppenheimer is not, so Born-Oppenheimer is not about neglecting electron-nuclear interactions. Because that would in fact be a disaster if you neglect this. But the Born-Oppenheimer is about separating electronic and nuclear degrees. So, since the title of this thing is the Born-Oppenheimer Approximation, and we have seen what we approximate because we neglect the first and the second derivative with respect to nuclear coordinates, remember? So that's an approximation. And obviously this approximation is not always good. And I will now not make a whole lesson about advantages, disadvantages of Born-Oppenheimer, when it is good or bad. Just I would like to give you a feeling or to tell you that in cases this approximation is not good, and I will say you when it might be not good. In cases it is not good, then there are ways how one can go beyond and improve on it. And this goes so. So the Born-Oppenheimer approximation is bad, or say its validity is reduced, whatever, so it's not a good approximation, whenever electrons nuclei have similar energy scales. So what do I mean with this? A picture explains much better than what it is. So imagine you have just one nuclear coordinate. For example, you have just two atoms, and r might be the distance between them. Okay? So in the Born-Oppenheimer approximation, we know that for each value of the distance, we have an electronic problem, we calculate its minimum, and this gives us our nuclear potential energy surface. But for this same value of r, okay, so we might have sort of here's energy, I have some energy value. But for the electrons, for this given value of r, we have a ground state, and then there are the electronic excited states. Obviously, we have a Schrodinger equation. Typically, we only look at the lowest solution, but there are solutions with higher energy. Okay? So there will be other solutions which might have this energy, and these, and so on, and there are different things. The same happens for each value of r. In principle, you have ground state, excited states, and so on. Typical values of these distances here, so for electronic scales, if you solve this, they are typically of the order of electron volts. Okay? So typically, I mean, might be half an electron, it might be 2 electrons, but so a typical scale for these things here are in the order of electron volts. While the typical, so for example, so if you look only on the ground state, this might be precisely something which looks like we have just said. Okay, so the ground state energy depends on the nuclear distance, and you might have something like this. The scale on which the nuclei have their energy, because they might be, for example, vibrating here, it's much smaller, because you see the nuclei might be vibrating in this minimum here. Okay, so the scale of electrons, the scale of the nuclear degrees of freedom energy, nuclei, they are typically in the milli-electron volt range. For example, a typical measure for how much energy the nuclei have is the temperature. Okay? Because nuclei move, the nuclear movement is what we feel as a temperature, and room temperature typically is 25 milli-electron volts, so it's in the milli-electron volt range. So much smaller, if you're not going to extreme conditions. Nuclei have a much smaller kinetic energy than the energy scale of this. So, and as long as you're in a situation like this, where whatever the electrons do is immediately involving energies which are much larger than the energy which your nuclei have when they are moving, then these two systems are very well, one says, decoupled, because they are different energy scales, and they decouple well, and Born-Oppenheimer is a super good approximation. So most of the time, Born-Oppenheimer is very good. But now it can happen, and this sometimes happens, that for example the excited states here, they might depend less on the nuclear, and these two things come very close. For some other nuclear distance, it might be that this gap here becomes very small. And then suddenly you end up in a situation where the electronic energy scale is also the order of milli-electron volts, like the nuclear movement energy scale. And if you're in such a situation, then there will be strong energy transfer between nuclei and electrons, and all these approximations we've done are less valid. So keep in mind that Born-Oppenheimer is very good as long as you have large electronic gaps. If the electronic gaps become zero, or if the electronic gaps even, they become small or become even zero, because even that can happen, then you are in a situation, and these things are then called intersections. Or conical intersections. So if the ground state of the electrons and the excited states, so the first non-ground state eigenvalue of your electronic electron is very close to the other, then we will have transfer between the degrees of freedom, and then Born-Oppenheimer is creating huge problems. Okay. So keep that in mind when you do these kind of things. In 99%, Born-Oppenheimer is a super good approximation, and there's no problem. In special cases, especially if you're doing photophysics or photochemistry, where, for example, you use light to bring an electron from the ground state to the excited state. Then your system might move under this here and might arrive at a point where it wants to go back to the ground. Then here you must be careful. It goes far beyond this course to tell you how to solve this in a computer simulation. If you're interested, you can look. A keyword you can Google for this is called, it's a Thule surface hopping. This is one of the numerical schemes how people solve it when they have to go beyond the Born-Oppenheimer. Why surface hopping? Because you see, this is one potential energy surface. Another potential energy surface where the electrons are not in the ground state might be this. And one might have to hop from one potential energy surface to the other, and this Mr. Thule has invented an effective way of doing it. I will not teach you here how to do Thule surface words. These are just things you should have heard about. Okay? So Born-Oppenheimer is, for all practical cases, you will encounter a very, very good approximation. It becomes bad in case you have two potential energy surfaces which come close to each other. Questions? Okay, very good. If there are no questions. So now that we have seen how we can get rid of this mixed nature of nuclei and electrons, we can now look at how we solve the electronic problem. Okay? So for a given nuclear coordinates, for example, if there are two atoms, for a given distance, how can we find out what is this value, what is that value? How can we solve the electronic Schrodinger equation? And I've promised you last time, I've said it many times, it's unfortunately a super complicated problem, even that. And for this, let's have a little look. Can I erase all this? Yes? Okay, so from now on, we are interested in the second equation, the electronic one. Okay? And I will now, in the following, when we are looking at the electronic wave function, so finally we can say now again the electronic structure problem. Not really a problem, it's as always a challenge for us. In the following, so this electronic wave function, which I called and I will continue to call phi, we know it depends on the coordinates of all the electrons. So on R1, R2, Ri, Rj, up to the number of electrons we have. Before I've also written that it depends formally also on all the nuclear coordinates, but we have seen that the nuclear dependence is just kind of as a parameter. There is no quantum nature in the nuclear thing, so in the following I will not always write. We know the nuclei are somewhere, and that's it. Okay? The quantum nature for our electronic wave function lies in these things here. I have already hinted to the fact that one of the problems we have is that we cannot just take any wave function which has 3n arguments and say we're looking for the function of 3n arguments which minimizes the expectation value of the Hamiltonian. Then the problem would be easier. But this phi here must be an allowed wave function. And we know it must describe n electrons, and we know that the electrons are all fermions and they are indistinguishable fermions. Okay? So this here, it must be a valid wave function for n identical fermions. Identical is a key word here, because identical means they are indistinguishable. You cannot say that this electron here is called Ralph, the other is called Peter, and then you know that if you exchange them, now Ralph is on the left and Peter on the right. No, they are exactly the same. There is no, since these are elementary particles, there is no way to distinguish one electron from the other. They are exactly the same. And therefore, these identical fermions must have, or give to this wave function a special thing. And that is, if you try to exchange them, you must get the same result, but with a minus sign in front of it. So we know this wave function here, it must be such that it is minus this same wave function if we exchange any two of them. So R1, R2, Rj, Ri, Rn. Okay? So if I exchange the two coordinates, I must get a minus sign. This is the complicated. I mean, we must also have that the integral over d3n r of phi star times phi is 1. Okay, so it must be normalized, but this is not so much a problem. But here, the Fermium symmetry, this is what is difficult. And this Fermium symmetry, it implies, as you have also learned, that our wave function satisfies the Pauli principle. What is the Pauli principle?
Two fermions can't have all the quantum numbers.
Exactly. So you cannot have two electrons in the same state. Otherwise, they would all go to the state which is lowest energy, like bosons would do it. No, in the ground state, you must have all of them in different states, and therefore, this is guaranteed by this, because the only way to obtain that they are in the same state would be that phi is equal to 0. So this is what enforces one, enforces the other. Okay? So this is what we must do, and whenever we look now for a solution of our problem, we must be very careful that we do not look for a solution which is violating this, because that is not only a bad approximation, it would not work at all. Okay? So the way how we start is the following. So we say we know we have Ne electrons, and now we place these Ne electrons, each one in one kind of wave function in space, okay, in a single particle wave function. So we say we have put them, place them into Ne, so-called spin orbitals. So we know that all electrons have spin 1/2, so they can be spin up or spin down, only two possibilities. And these spin orbitals, we call them the phi I of R, of R and C. Okay? So this here is a single particle wave function. It's kind of the wave function like you've learned for the hydrogen atom or for the harmonic oscillator or whatever. It's a function which depends only on the coordinates of one single electron. So this is why it's a single particle wave function. Sigma is simply a variable which can have two values, up or down. Okay, +1 or -1 or whatever. This indicates if you take it as spin or not. So you have a shape in space. Okay, you say in this kind of shape, which might be localized around this chair here, but going to 0 away from it. So phi I, the R dependence, gives you the shape in space. And with the sigma, you say if it's 0 when it's a spin up or a spin down. Okay? So you define for the electron, for every electron, a spin and a shape in space. And how many of them do you need? Well, you need as many as you have electrons, and you put one electron in each one of them. Okay? So, and we assume they are orthonormalized. So we choose them such that phi I times phi j is delta ij. Also sometimes, because people are always lazy in writing, one does not like to write something is a function of r and sigma, so of point in space. So one makes a shortcut notation and calls this x. So sometimes one writes phi of x, and means with x that means coordinate in space plus the information spin up or spin down. So if we have n electrons, we need n orthonormal single particle functions like this. And then also just, if you read some papers or some books on these kind of things, one calls typically alpha spin is spin up, and beta spin are such which are spin down. Now we put the n electrons, each one, into one wave function for itself. We have made sure that they are orthonormal, so you do not have two which are in exactly the same, for example, one S wave function. Okay, so all this is good. But now we have to ensure this. And one way to ensure that you have the right fermionic rule is not to write the total wave function, the capital phi, as phi 1 times phi 2 times phi 3 and so on, but to write it, you have seen it certainly already, as a determinant. Okay? So this is, and I will write it only once, it's in its complete form. So the fermionic symmetry is satisfied if the capital phi, so the many-body wave function, has the form of a Slater determinant. Slater determinant would look like this. So we would have phi of R1 to Rn is like the determinant of the following matrix. Phi 1 x1, phi 1 x2, phi 1 x3, phi 1 xn. And then this continues here up to your phi n x1. Why have I done this? Because here you see that, so this first of all is a square matrix, okay? Why is it square? Because I have n spin orbitals from 1, phi 2 up to phi n, okay? So I have n orbitals, I have n electrons, and I change always here for each of the orbitals by going from one row to the next. I'm changing x1, x2, x3 to xn. So there are n electrons, n orbitals, so it's a square matrix. Of a square matrix, we can always calculate its determinant, and this determinant is what is our many-body wave function. Okay? So it is not, so this wave function is, I will remove it in a minute, it is not what one could have hoped, phi 1 of x1 times phi 2 of x2 times and so on up to phi n of xn. That would be nice, because then you have simply your total wave function as a product of single body wave functions. But no, this term here, it appears in the determinant, because you have this times this times this times this. This here is one of the terms, but then you have plus or minus, for example, phi 1 of x2 times phi 2 of x1 and so on, phi n of xn. So you have all kinds of different orders of these things which appear here. So a determinant is a sum, always with a strange sign in front of it, of all kinds of different orders of arguments and functions. But one thing which all these terms have in common is that no wave function appears twice. So you have always in each term the n different wave functions appearing and the n different coordinates. They all appear always. Only the order is changed in a complicated way in a determinant. So why do I say that a determinant is what we need? Because it has the right properties. So if I now exchange particle 1 with particle 2, okay, so I exchange, for example, x1 with x2, it is as if I exchanged in this matrix row 1 with row 2. Okay? So exchanging two rows in a matrix means for the determinant that the determinant changes sign. So it's this mathematical property of a determinant which is what we want. Also, if you have, for example, two particles in the same single particle orbital, which Pauli would forbid us, then you would have, for example, phi 1 is equal to phi 2. But if you have a matrix where you have two columns which are the same, then the determinant of this matrix is also 0. Okay? So the nice thing about this is that all these symmetries which you need for fermions, if you have a determinant, they are satisfied. Okay? So we will have to look, therefore, for solutions in the form of determinants. But I should already say here, this is not what makes everything so complicated. What makes everything so complicated is that, yes, a determinant is an allowed wave function. This is no doubt. But it does not mean that the real wave function is a determinant. It goes one way, but it does not go the other way. Why not? Okay, so if your wave function is a determinant of a matrix, like I've written here, then we are fine, and this is certainly, by all means, an allowed fermionic many-body wave function. But, just to give you an example, a sum of two determinants, of two different determinants, has exactly the same properties. Okay? So a sum of several determinants is also an allowed wave function. And nature is unfortunately not kind enough to us to make such that the ground state electronic energy is given by a single determinant. No. The real wave functions that we have to look for are sums of many, 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 many possible determinants. And this is what makes things so complicated. We will in the next lesson we will talk a lot about this. But right now let's just focus on one determinant. But keeping in mind that the real solution which we are looking for will be this determinant plus another determinant plus another determinant and so on. Okay, so let me now just say one thing we will need later to manipulate determinants. So one way of writing a determinant is by this square and putting a determinant sign here. But another way of writing a determinant, and this will be important for the future, is by writing the determinant is a sum over p. I will explain what all this means in a minute. Minus 1 to the power p. And then we have phi p of 1 of x1, phi p of 2 x2 up to phi p of n of xn. Okay? And here I've made a mistake. In order to be this, here one has to 1 over square root of n factorial, otherwise this is not normal. So here also we have 1 over we're looking for. So what do I mean with this writing of a determinant? The sum over P is the sum over all possible permutations. Okay? So a permutation is if you have n numbers from 1 to n, say for example we have 4, we have 1, 2, 3, 4. And now in how many ways can you write the numbers from 1 to 4 such that all numbers appear? Okay, so permutations of this might be 1, 2, 4, 3, 1, 4, 3, 2, 1, 4, 2, 3, 2, 3, and so on. So a permutation is a reordering of the numbers from 1 to n. Okay? This sum here is a shorthand notation of we are summing over all possible ways of ordering the numbers from 1 to n. This is what is meant with this here. The minus 1 to the power p means if it is a so-called even permutation, we have a plus sign. If it's an odd permutation, it's a minus sign. Even or odd is determined by how many times you have to exchange two numbers in order to arrive at the given permutation. Okay? So even odd permutation have a plus or minus sign, and then you take phi of the first number of x1, phi of the second number, so you have all kinds of combinations of orders of spin orbitals with the arguments there. Okay? So this is what a determinant is, and we will have to look at a lot of determinants in the next lessons. So far you follow me? Okay. So, as I've said, we now try to solve for phi. We do not care about nuclei anymore because the nuclei are just the parameters for us. We care about the electronic part. Electrons are identical fermions. Therefore, when we exchange, we must have a minus sign and we must not have two in the same state. That is a property which is satisfied by a determinant. So we can look for a wave function in the form of a determinant, and we will obtain a valid wave function. But keep in mind, our problem will be that the sum of many determinants is also a valid wave function, and in nearly all physical cases, the real ground state wave function we want to find is the sum of many determinants. Okay? So, now, before we finish, I would like to play in the computer. Let's see if it works. So perhaps I switch off this. Goodbye, YouTube.